this video I wanted to discuss the concept of angular momentum. We've already discussed how linear momentum can be found by multiplying an object's mass by its velocity. In all of my rotational motion videos, I've explained how the formulas are really nothing new, but just the rotational equivalents of the linear formulas that you already know. The same holds true for angular momentum. I've already discussed how an object's moment of inertia can be thought of as the rotational equivalent of mass. And we know that angular velocity is the rotational equivalent of translational velocity. Therefore, we can write angular momentum, represented by uppercase L, as an object's moment of inertia multiplied by its angular velocity. This is true for any symmetrical object rotating about a fixed axis through its center of mass. Previously, I've shown how the net torque on an object is equal to its moment of inertia multiplied by its angular acceleration. We can actually rewrite this in terms of angular momentum. Because angular acceleration is equal to the change in angular velocity divided by the change in time, we see that this just becomes the change in angular momentum divided by the change in time. This formula shows us that if the net torque on an object is zero, the change in angular momentum will also be zero. In other words, angular momentum will be conserved. This is the equivalent to how linear momentum is also conserved when no net force acts on an object. We can say that an object's initial moment of inertia multiplied by its initial angular velocity is equal to its moment of inertia multiplied by its angular velocity at any other time. This is only true if the net torque equals zero. To better understand conservation of angular momentum, let's use a real-world example. Pretend that this poorly drawn stick figure is a figure skater spinning on one foot with their arms outstretched. The person will have an initial moment of inertia and an initial angular velocity. Now let's say that the figure skater tucks their arms in closer to their chest. This might not seem like it will have any effect, but it will. By doing this, they're bringing more mass closer to their axis of rotation. If you remember that an object's moment of inertia is equal to the sum of every point's mass multiplied by its distance from the axis of rotation squared, you'll see that this will affect the figure skater's moment of inertia. Because some of the figure skater's mass moves closer to their axis of rotation, we see that the moment of inertia will actually decrease somewhat. And because angular momentum must be conserved, the figure skater's angular velocity will need to increase. This is how figure skaters are able to spin extremely fast. The same is true for a person trying to do a backflip or a front flip. You'll see them tuck their knees in closer to their chest to concentrate more of their mass closer to their axis of rotation. I hope that this video allowed you to understand angular momentum at a basic level and see how important it is. In my next video, I'll go over a numerical example using this concept. However, if anything was unclear to you in this video, let me know in the comments below. If you found this video helpful, please give it a like and consider subscribing to the channel for more fast physics videos. Thanks for watching.